Hi there, and welcome to Telefunken. Today's video is one in a series on the vintage Roland CR8000 analog drum machine. In this episode, we'll take an in-depth look at the power supply in the CR8000. We'll be converting the power supply in a machine that was manufactured for the European market, where the domestic supply voltage is around 230 volts AC, to one that will be suitable for use here in North America, a jurisdiction that supplies a nominal 120 volts AC. We'll also be making a few improvements to both the safety and performance of the power supply that could be broadly applicable to some of the vintage instruments in your own personal collection. If that sounds interesting to you, stick around. The schematic for the power supply in the CR8000 can be found on page 6 and 14 of the service manual, and the supply itself is on the CPU PCB with the transformer and power switch mounted separately. The power supply produces 3 independent rails of smooth DC, +5, +15, and -15 volts. It's a relatively straightforward linear supply with a couple of components that might be hard to source if something should go wrong, and we'll describe these in a moment. AC power enters the instrument through a polarized grounded connector that's subsequently wired in one of 4 configurations depending on the destination market. The line cord is immediately fused before proceeding to either a single pole switch in North America or Japan, or a double pole single throw switch in Europe and the UK, where both the line and neutral are switched in unison. Directly across the AC line lies C101, a 10 nanofarad 400 volt capacitor that acts primarily as an interference filter, preventing reintroduction of noise into the line. Notably, this capacitor is before the power switch and sees the line voltage whenever the instrument is plugged in, even when the instrument power switch is in the off position. Given that this capacitor is more than 40 years old and predates the development of modern safety capacitor standards, this is one of the first components we'll be replacing. Power proceeds from the switch directly to the power winding of the power transformer, which in our case is a Roland part number 2450242D, with the D denoting the transformer for the European and UK markets. The correct transformer for the CR8000 here in North America is 2450241C, the transformer for 120 volt service, and for Japan the correct part is 2450240N for 100 volt service. Each of these transformers have 2 independent secondary windings that provide independent AC sources that power the 3 main DC rails used in the instrument. As we'll be converting this instrument for use in North America, we'll be dispensing with the power cable, the aforementioned capacitor, and the transformer, reusing only the power switch and the PCB housing the line capacitor and fuse in this part of the power supply. After passing through the power transformer, the secondary's outputs are connected to the CPU board. One secondary winding provides a nominal 10 volts AC at 700 milliamps that's regulated to provide 5 volt DC supply for the CPU and the logic circuitry. The other secondary provides 23 volts AC on each side of a center tap at 120 milliamps, which is regulated to plus or minus 15 volts DC to power the analog sound generation circuitry. There are secondary fuses for each AC source before they're sent to their respective integrated full bridge rectifiers, which convert the AC to DC. The rectified DC is then smoothed by 1000 or 470 microfarad electrolytic capacitors before being regulated to maintain the target 5, positive 15, and negative 15 volts. Voltage regulation is accomplished in the first case using the Jelly Bean 7805 voltage regulator, which further smooths the DC. The 7805 regulator is mounted off-board on the instrument chassis, which acts as a heatsink. The 15-volt rails are a bit more complicated. In this case, they're regulated by a Toshiba 7179P voltage regulator IC, which controls PNP and NPN pass transistors, again mounted off-board using the chassis as a heatsink. The 7179 is out of production, so if this chip is damaged, you might have a hard time replacing it, unless you're able to find genuine old stock on eBay or elsewhere. The pass transistors are TO220 packages, and though the transistors themselves are now obsolete, they could be replaced by any number of suitable alternatives. In this video, we'll describe a number of changes we'll be making to ensure that this instrument continues to operate safely for years to come. All of the electrolytic capacitors in the power supply will be replaced with new capacitors. We'll replace all of them as they're more than 40 years old at this point. We'll also be upgrading them slightly. Those of you with a keen eye will notice that some of the electrolytic capacitors on the 15-volt rails are only rated at 16 volts. That's a little close for comfort, so we'll increase the voltage ratings in these capacitors to give them a bit more room to breathe and ensure longevity. We'll also make sure the initial smoothing capacitors are rated at 105 degrees Celsius, which will certainly help. We'll be replacing C101 with a more modern X2Y2 safety-rated capacitor. Safety capacitors are manufactured in such a way that they're guaranteed not to fail short, unlike the capacitor that's currently in the instrument that does indeed have that potential. But before we get started, we'll need to find a suitable power transformer. The transformer shown in the schematic has two independent secondary windings, one with a center tap. This configuration with these voltages is not unusual. It's common to find transformers with duplicate or center tapped secondaries providing two windings at one voltage and another secondary providing a second lower voltage. In audio equipment, this configuration is useful and can be used to power op-amps and the like from bipolar rails while allowing for a second low voltage supply for logic circuitry. The transformer we'll use is an R-Core transformer designed for low noise applications such as precision headphone amplifiers. With dual primary windings, it can work with either 120 volts or 240 on the primary and has a center tapped secondary providing a nominal 15 volts aside at 700 milliamps each and a single secondary providing 9 volts at 1 amp. These are loaded ratings, giving us plenty of room to use each of the 15 volt secondaries to generate our positive and negative 15 volts DC, and the 9 volt secondary will be used to generate our positive 5 volts. The transformer we've selected is rated at 30 volt amps, which is plenty for our application. Before we get started, I wanted to share a few words of caution. Although generally safer than their switch mode counterparts, linear power supplies do contain line level voltages that could be dangerous. Please do not attempt any of this kind of work if you're uncomfortable or don't know what you're doing. Even the most simple circuits can offer up surprises. So, if you're going to attempt any of this type of work, take your time and stay safe. Let's dig right in.
So the first thing I would do is I would check to see that the power is actually coming from this end of the cable to the transformer. And the way that I do that is use a voltometer and see if I can measure across the primary windings of the transformer from this end of the power cable. And if I attempt to do this, I get an open circuit on my voltometer. That's not surprising because the power is turned off. And so there should be no connectivity between this end of the plug and the transformer because that's what this switch is for. So when I close this switch and I recheck for conductivity, I still have an open circuit. So how can that be? Well, I've already checked the fuse, the primary fuse, which is located beneath this panel here, and it's good. So what else is there? Well, all there is in between this end of the cable and the transformer is this switch. So either the transformer winding is open or we have a dud switch. If we probe across these two wires here, the white and the brown wire, which go to the transformer, and we measure the resistance there, we see 152 ohms. That is the resistance of the primary winding. So the transformer is not open. And if we look at the secondary windings, we can see across this secondary winding, which supplies the positive and negative 15 volts DC once it's rectified, we see about 12 volts. Between the here and here, we see about 12 ohms. And between the center tap and one side of the secondary, we see 6.5 ohms. And between the center tap and the other side of that secondary, we see about 6.5 ohms. So that makes sense. And across this secondary, we see very low resistance, about 1.2 ohms. We'll have to come back to that. If we close the switch, we should have connectivity between here and here, and we do not. No connectivity. Similarly, here, between the white and the white, we should have connectivity, and we do not. So we apparently have a dud switch. So we'll take this switch out and have a look at it. So here's our switch. It's a, you can tell by this little logo here, it's a Matsushita or a Panasonic switch from the SS13 series, ESB70294. Now these are not made any longer, and so these have to be acquired through new old stock if they can be located, or as might be the case in this example, they need to be repaired. And so we are going to now attempt the disassembly and repair of this switch. Here we have our little switch, and we'll attempt to disassemble this in an effort to clean it. Now, I find that oftentimes strangely, the easiest thing to use to disassemble things like this, to peel back these little tabs, are a pair of cutters, which of course you obviously don't want to apply so much pressure so as to cut anything. But nonetheless, they give a lot of control and leverage, and so I use them, so sue me. So see how easy it was to do that, to peel these back? You can try to use a screwdriver, something like that, but this works very well. So there we go. What's inside this? Whoa! Well, that's what's inside it. So the business end of this switch is located inside here, and it consists of these little elements here that rock back and forth. And they contact this little element right here, which is so gummed up, it's almost black actually. And it looks like maybe it's had a little bit of arcing going on in there. So normally what I use to clean contacts is this, which is a fiberglass bristle brush. And I'll give that a shot, but I think this may require something a little stronger. And this is actually not going to be able to get in there very easily, but I can extend it, so we'll give that a shot. I don't know if you can see that, but some of this black gunk is indeed coming off. I'll put some isopropyl in there. So that's just a portion of what's come off this one contact. Pretty filthy. And with any luck, you can see the difference between the two. This one's been cleaned, obviously. That one has not been cleaned. And again, this contact is black. This is now deoxit, which is considerably more chemically corrosive. But I'd like to get all of the oxidation off of this, and so the deoxit will help with that. I don't want to leave a lot of deoxit residue because it will attract dirt and debris, so I'll be washing it off. But you can see how that's cleaned that up a bit. I'll put a little deoxit in here, but then again, I'll be rinsing it out. I'll rinse this out quite thoroughly with a squirt of IPA to make sure there's no glass fibers in here. I'll just take a couple of pictures and make sure that I get a decent image that I can share with you. Well, here it is. After quite a bit of faffing around, I managed to get this switch back together. Which was no small feat, given the fact that what kind of makes it work is no fewer than 5 different spring-type elements that are, well, I guess 6, including this little guy here, that are part of the mechanism. So it is working. It's a push-button switch, and it's been cleaned, and just to confirm that in fact it is working, we'll just connect the voltometer here and close the switch, and we see that we have connectivity or conductivity across these 2 terminals, and similarly across these 2 terminals. So That was a lot of work. It took me maybe about an hour or so actually to get this back together. It's like mechanical origami. One might ask, well, why don't you just get a replacement switch? Well, first of all, I don't know where to get such a thing. We'd be looking for new old stock. But just as a hint to anyone who might find themselves in a similar predicament, if you're not able to repair this type of switch, this switch made by Matsushita was also used in various forms as a power switch in stereo receivers made by companies like Marantz, I think Pioneer, Kenwood. And then the version of this power switch, well, it's not even this power switch, it's another switch made by Alps. It was actually the power switch in the US versions of this instrument. So there are other switches that can fit, but of course you'd need this geometry where you can mount it to the bracket on the instrument and have the appropriate length of travel and so on and so forth. But while this is a double pole switch for the European market, the switch used in North America and in Japan is a single pole switch. So it's the Alps switch as opposed to this Matsushita switch. So I don't know if that's particularly helpful. I apologize. I wasn't able to film the actual reassembly. It was, it went on and on and on for quite some time. And I didn't know if I was actually going to be able to get it to all fit together and work properly because of the multiple parts that had to be interconnected in just the right way in order to reconstitute this mechanism. But there we are. So the question is, if this instrument was getting absolutely no power by virtue of this switch failing, what else, if anything, is wrong with it? Well, I'm tempted to reinstall this switch and just turn the thing on and see if it works. But I'm also mindful of the potential for all kinds of other failures. So I will still be disconnecting the power transformer, confirming that it's working properly, and then evaluating the power supply before I actually reconnect the voice control boards and the switchboard in the instrument. So that's that soldered back in. I didn't bend any of the leads over because in all likelihood, as I'm replacing this transformer, I'm going to be desoldering this switch at a later point. So this is a temporary installation. Okay, so what I've done is I have connected my Variac isolation transformer and electronic circuit breaker to the input, the power input for the transformer using this connector, which is an AC male plug, which is connected to some alligator clips, also known as a suicide connector. And this is clamped onto the point where the power cord comes into this little printed circuit board and then goes through the fuse and the switch, of course, before going through the transformer. Then I've connected the secondary of the higher voltage winding, which is supposed to be providing, according to the service manual, plus or minus 23 volts. And it's really AC power, so I would assume that really what we should be looking for here is 46 volts, the sum of that, in the case where we connect this to 240 volts. However, my Variac doesn't go up to 240 volts. It only goes up to 130 or so. So I'm going to be setting it at 120 volts. So if the universe unfolds as it should, we should be getting about 23 volts AC out of this transformer at 120 volts, more or less. So I'll turn on the Variac. And this piece of equipment is featured in a video on my channel. If you're interested in getting a closer look at it, it's something that I built myself. And I'm now going to turn on the power with the power switch. And indeed, we get 22.8-ish volts when we're putting 120 volts into the transformer. So this winding appears to be operating as expected. I will just gingerly reposition for the center tap winding, and we should be getting about half that. And we're getting about 11.4 or so, which is probably just fine. I'll turn this off, reposition the leads, and these yellow wires are the other secondary that is supposed to be yielding about 10 volts AC. And then this is used to derive the 5-volt power supply. So nothing's touching here. So with 120 volts input, we should be getting about 5 volts AC here, assuming the transformer is working as it should. And we're not. Aha. I suspected as much. The resistance of this winding was much lower than I had expected. And accordingly, I don't believe that this instrument would have been working. And I think that there's a problem with this transformer. We'll check that once more. Yeah, 0.3 volts. That's not going to do it. And so really there's nothing else other than the switch and the fuse in between the transformer and our reading here. And so this transformer is damaged somehow. And it's damaged in such a way as the winding that would be deriving the 5 volts is not giving us enough voltage to get that 5 volts for the supply. So another failed component that will need to be either fixed or replaced. In terms of fixing a transformer like this one, and I'll turn off my Variac as I go poking and prodding with my fingers. The only fix possible for something like this might be if one of the windings, or rather the winding was exposed in such a way that we could see a break in the winding. That's really unlikely given the composition of this transformer, the way that it's constructed. And because this is a 240 volt transformer anyway, I think that our best strategy here is to replace it. And indeed, I have a R-core transformer on order from overseas that I will be installing into the instrument as part of the conversion to the 120 volt standard here. So what do we do in the meantime? Yeah, this is another failure, but there could be more. And hopefully our damaged 5 volt winding hasn't taken out some of the components on the CPU board that rely on that 5 volt supply. That would be a real shame. I can test the power supply section of this board by injecting AC voltages into the appropriate points on the board. And that's something that I'll be doing next as a way of pursuing the repair of the instrument overall. I am set up to examine the performance of the 15 volt portion of the power supply on the CR8000. And what I've done is I've pulled a transformer from my supply here, which isn't necessarily a replacement transformer for the one that's in this instrument, but it is a transformer that I can use to generate a 46 volt AC supply with a center tap, giving us 2 times 23 volts, which is what this instrument is expecting. And so I've set this up with a suicide cord connected to my Variac, so I can adjust the input voltage to the transformer. And then we're monitoring the output voltage across the secondary winding. And I've connected the secondary winding to the section of the board in the CR78 that's expecting the 23 volts on either side. And I have connected another voltmeter to pins 29 and 30 on the CR78 CPU board, which is where the power leaves the power supply and then goes to the voice generator board. And that's shown in the schematic in the service manual. We can also access pin 31 adjacent to pin 30, and that's where we should see a negative 15 volt supply. Pin 32 would give us 5 volts, but that's contingent upon us supplying a 10 volt AC supply to pins 24 and 25 on the CPU board, where the supply then goes into the bridge rectifier. So this may be a little dangerous. I haven't checked the integrity, for example, of the bridge rectifier or anything like that. I've set the electronic circuit breaker with a very low cutoff, meaning that if there's too much power drawn, it will immediately shut off. And so we shouldn't be damaging anything. And I'll turn that on right now. And what do we see? We see that we've got about 46 volts here across the secondary, and we do indeed have a 15 volt, positive 15 volts at the appropriate pin. So the positive 15 volt portion of the supply is working as it should, which is good news, meaning that this portion of the circuit here is working, including presumably the bridge rectifier, this pass transistor, and this integrated circuit, which is not so easy to find if it's not working. So I'll turn off the Variac and I'll move over to pin 31, which is the pin that should be presenting us with a negative 15 volt power supply, if indeed that portion of the supply is working. Turn the Variac back on, and that's exactly what we have. We have negative 15.01 volts, and that is really terrific news. It means this portion of the power supply is working. If we move over to AC, for example, what do we have? We've got about 12, 9, 10, 8 millivolts, 7 millivolts ripple on this supply, and that's probably a little more than I'd like to see. I'd like to see maybe 1 millivolt of ripple on the AC supply. So we'll deal with that when we recap the supply, maybe put in a ceramic cap across our electrolytics, try and bring that down a little bit. Let's check the AC ripple on the positive 15 volt. Turn off the Variac, move this over, turn the Variac back on. We've got 15.07 volts, and we're measuring, in terms of AC ripple, maybe 10 millivolts or so. Not terrible, but again, much higher than I'd like to see, I'd prefer to see. So we'll see about addressing that. If we look at the filtering on the output of this supply, we see that we have we've got a number of electrolytic capacitors. So this one appears to be a 220 microfarad at 16 volts on the negative rail. And then we have another 10 microfarad electrolytic, and we have a 0.1 microfarad film capacitor. These are these green things right in there. And then here on the positive, we've got only a 10 microfarad cap and a 0.1 as filters on the output. In terms of reservoir caps, we have two 470 microfarad capacitors rated at 25 volts, which is maybe a little too close to comfort given that we're pumping about 23 volts into them. So when we recap, we'll probably increase the voltage ratings there. On the 5 volt supply, since we're looking at the schematic, we've got a 1000 microfarad at 16 volt reservoir cap, which is a little better in terms of the voltage rating. We've got 10 volts coming into it. So that gives it a little bit more headroom, which is nice. 1000 microfarads is pretty hefty. And then on the output, we have a 10 microfarad at 16 volts and a 0.1. And again, this will probably benefit from a ceramic across that. Ceramics get rid of some of that high frequency stuff that tends to come through lines as a result of the predominance of or prevalence of switchbone power supplies in our current modern day environment. Alrighty, let's see what we can do about this plus 5 volt supply, see if it's working properly. And that will require injecting 10 volts AC into pins 24 and 25. And in this case, we do not require a center tap. One of the ways to do that would be to simply use this transformer again, or I could use the auto transformer in the Variac. I'll just use this one and turn the Variac down. Okay, we're set up to examine the 5 volt rail, and I've connected this transformer output to the input of the power supply, pins 24 and 25, where it expects to see 10 volts AC. And I've disconnected one of the connectors from the transformer for the moment, but I do have a voltometer showing that we now have 10 volts AC presenting itself at the output of the transformer. Turned my variac down to generate this voltage. We're also connected now to pin 32 on the board, which is where the 5 volts should be presenting itself. So I'll connect the board, and see if we get 5 volts. And we do not. We do not get 5 volts. And so that suggests that we do have an issue with the 5 volt portion of the power supply. Could be a number of things. One of the things that could fail is this 7805, which is a voltage regulator, IC13, which is meant to regulate the voltage. But the fact that we're not getting anything suggests another failure. It could be, for example, the bridge rectifier. The board will need to be pulled in order to diagnose this properly. So I've pulled the CPU board out of the 8000 and configured it so that we can test the 5 volt power supply. We're attached to pin 29 here, ground, and pin 32, which is the 5 volt rail. And I've got a voltometer connected there. And we have power that we're injecting into pin 24 and 25, where the approximately 10 volts is coming in AC, gets rectified, filtered, and then regulated with this 7805 regulator. And what I have found is that if I turn on this voltmeter, which will be monitoring the input, and I use an AC adapter that I have here, which outputs an AC voltage, I find that if we inject 13.5-ish volts AC into the system here, where it's expecting about 10, it regulates it to 5 volts. So this is working fine. And all that I've done is I've taken the board out. The regulator is getting a little warm because it's having to regulate an extra 4 volts or so over what it was expecting. I'm now going to disconnect this so as to not damage anything. But I haven't replaced any parts or anything. All I did is remove the board. Notwithstanding, we'll be recapping this, cleaning it up, and taking a real good look at the bottom of the board where there's quite a bit of corrosion, and also testing all of these transistors to make sure they're okay. The capacitors that are in the power supply are 1000 microfarads at 16 volts, 470 at 25, 220 at 16, etc. In my opinion, this 16 volt capacitor rating is too close to comfort, given that we have a 15 volt rail here, a plus and minus 15 volt rail. So we'll be upgrading the voltages on these slightly, but other than that, we'll be using the same values. Well, this is the power supply section of the CR8000, and I've made some modifications in order to convert this to the North American voltage standard. I've replaced the power transformer with this R-core transformer, which is a dual voltage transformer, but one of the taps, the 230 volt tap, is not going to be used. We're just using the 115 volt tap, and it's going to produce 15 volts on each side of a center tap, and then 9 volts, which will be used to drive our plus or minus 5 volt supply. I've put in a polarized 3-prong plug, taken the grounded it to chassis, and grounded the shield of the transformer to chassis. I've also made a modification on the board that houses the fuse and the capacitor. This capacitor, which is only rated at 250 volts, it's a 10 nanofarad capacitor. It is across the AC line all the time. no matter whether the instrument is switched on or not. And so what I've done is I've replaced it with a proper X to Y2 safety capacitor. And I've put another safety capacitor after the switch. This safety capacitor is before the switch. This one is after the switch. And this may cut down on the arcing inside the switch, which contributed to its failure, which is one of the reasons why this instrument wouldn't turn on at all prior to our repairs. Because the transformer wires themselves are not quite as long as the ones on the stock transformer, what I had to do is drill 2 holes here and put grommets in, which shortens the path slightly so they don't have to come all the way around here, passing by these pass transistors, which are part of the plus or minus 15 volt regulated supply. So I thought I'd show you this real quick. It involved a little bit of measuring and drilling to ensure that I was going to be able to put this back in place. I contemplated trying to position the transformer elsewhere in the instrument, but really there was no room. So what I did is I mounted it with 4 holes here, which have bolts going through them. And I had to move one of the feet, one of the rubber feet, and attach it to the bolt, one of the bolts that's securing the transformer. So I'll put this cover on and then test the transformer windings, make sure everything's wired up okay before we connect it to the CPU board, and make sure that the power supply is functioning as it should. We have the power supply plugged into my Variac isolation transformer and current limiter, and we've connected the voltometer to the winding that is to produce about 10 volts nominally under load, and we see that we're measuring 11.9 here. We'll turn that off and come over to the other windings. And here we should see roughly 30 volts from side to side. It'll probably be a bit higher than that unloaded, maybe as high as 36 or so. Oh, even higher than that, so about 40. And if we measure from the center tap, we've got about half that. Okay, so we're all set, ready to go. We can put the CPU board back in the instrument and see if the regulated power supplies are functioning as they should. We're connected to pins 29 and 30, which should be the positive 15 volt rail. And we have the CPU board in place and connected to the power supply. And there we are, we have 15 volts. I'll turn the power off, move over to the next pin, and this should be our negative 15 volt supply. And indeed we have negative 14. And we'll turn this off. And we'll move over to the 5 volt supply. And this seems very stable, with about 2 millivolts of ripple on the 5 volt rail. Come back to the positive 15. There we are. We've got about 3 millivolts of AC ripple, less than that, 2.5. Let's come back to our negative 15. Again, quite stable. And about less than 3 millivolts of ripple. Okay.
Well, that's all for this installment in our series of videos on the CR8000. Our new power supply is working great, and we're ready to move on to the rest of the instrument. To recap, so far we've replaced the faulty power transformer, fixed a broken switch, replaced the power cord and line capacitor, and installed a safety capacitor across the power switch, and replaced all of the old electrolytic capacitors with new ones, upgrading the voltage and temperature ratings slightly to ensure a long life. We've also replaced the fuses in the instrument to those with appropriate ratings for use in North America. The fault in the 5-volt circuit was resolved through simple disassembly and reassembly, suggesting a possible short caused by incorrect mounting of the 7805 regulator. We now have the proper voltages and about 2 millivolts of AC ripple on each rail, acceptable for our purposes, and that's without adding any ceramic capacitors to the power supply. The faults we've uncovered here in the power supply were more than enough to keep the machine from working properly, but that doesn't mean we don't have more work to do to fully repair this machine. In our future videos, we'll revisit the diagnosis and repair of this instrument, as well as the subject of MIDI kits, and we'll even design and install one we make ourselves. We'll calibrate the instrument, and we'll show you how to repair faulty momentary switches in the CR8000. Whether you're watching to learn more about your own CR8000, or just because you're interested in these machines, I hope you enjoy this series as much as I did making it. And as always, your comments, feedback, suggestions, and questions are most welcome.